Hi, so I'm Maria. I just finished my master's in Uppsala University, Sweden, and I'm going to present my master thesis project on the prospects for detecting quark star features with IceCube. Let's see. So the main objective of this project was to study the capability of IceCube and also IceCube Gen 2 to detect sharp neutrino features from the hadron to quark phase transition that can be present in the formation of a quark star. And now you might be wondering, okay, but what is a quark star? A quark star is a theoretical, for now, compact object, so a remnant of a star that has burned all its nuclear fuel, which is composed by deconfined quark matter. So instead of the typical neutron star composed by neutrons, hadronic matter, we have a smaller, more compact object where the quarks are just going around in a soup. We can use the neutrino signal from the quark deconfinement to identify such stars. And where do they come from? They come from a specific type of core collapse supernova, also theoretical for now, which are basically regular supernova, but with two collapses of the cores instead of one. I'm going to go through this again because they already told us a little bit about it. So massive stars with main sequence mass over 10 solar masses can produce extended iron cores after burning all the nuclear fuel that they have. So here in this situation, the pressure that was being made by nuclear reactions gets lower, and then gravity can overcome this pressure, so the core contracts due to gravitational collapse. Here, the densities in the core are so high that neutrinos get trapped interacting in the core because their interaction length is lower than the radius of the core. So here we have a regular collapse of the supernova. If we zoom into the core, we will see the core collapsing and then a shock wave going outwards after the collapse of the core. And this shock wave is reducing the density in the outer layers of the core in some places called neutrinospheres. And this makes the neutrinos that were trapped there from the previous nuclear reactions to escape, because density is low enough, so now the interaction length is higher than the radius of the core. At this stage, as we have been told today, we are left with what we call a protoneutron star, which is basically a compact object made mainly by neutrons, but not only. And then each neutron has two down quarks and one up quark, which is going to be important for the next phase. So here we have a regular supernova. And what can happen if the progenitor is massive enough? So in other words, we have a really high density in the protoneutron star. Something called a hadron to quark phase transition can be triggered, which is basically the quarks that were forming each neutron get deconfined. So instead of the barriers between neutrons disappear, and then they form, I don't find the, well, here. They form what we call a gluon quark plasma. So here we are seeing the formation of the quark star. When this phase transition happens, let's say the distances between particles gets lowered, so the gravity can contract the core once again. So we have a second contraction, and as a result, just as previously, we have a second shock wave that also reduces the density of this core, of this quark core, enough so that neutrinos can escape. In this case, it's mostly antineutrinos, electron antineutrinos, because the progenitor or the protoneutron star is less lepton rich than the iron core that we have at the beginning. So this secondary neutrino burst is mainly composed by electron antineutrinos, which is really nice for detection. So in IceCube, we can detect such neutrino signals, IceCube is a 1 kilometer cube neutrino observatory in Antarctica, where we have 5,000 digital optical modules developed, put in 86 strings, as we can see here in this graph. And we detect the neutrino-induced Cherenkov radiation. So we detect photons in these digital optical modules. So what we would expect to observe, 2 peaks, one from the regular collapse, so the regular supernova emission, and then another one from the second shock wave, which is going to be a higher energy and higher luminosity. Well, not really super higher energy, but just a little bit, but much higher luminosity. This secondary burst of electron neutrinos can be detectable via inverse beta decay, so one of the best channels that IceCube has, because we will see the electron neutrino interacting with a proton in the ice to give a positron and a neutron. This positron is going to travel higher than the speed of light in the medium, so in the ice, producing what we call Cherenkov light that is going to get to the optical modules and light them up. I'm also going to check IceCube Gen 2, which is basically IceCube but bigger and with better optical modules. I'm not going to go into details about it, but yeah. So now let's see what happens when we simulate such a core collapse supernovae and the detector configurations. So first of all, Evan O'Connor in Stockholm University helped me to simulate this weird core collapse supernova, where we are including a flexible equation of state module, so we can have hadronic matter and also quark matter in the equations of state of the supernovae. And we chose to analyze 2 progenitors, one a 30 solar masses progenitor that ends up in a quark star remnant, and another more massive that exceeds the mass that the equations of state can handle. So after the second collapse, it goes into a black hole. So it's a delayed black hole because it happens after the second collapse. But I'm just going to present the first one in the purpose of time. Then I use Asteria, a tool for simulating the IceCube and IceCube Gen 2 supernova response. So we are basically measuring how much the flux of neutrino is going higher, because we cannot measure specific neutrinos at these lower energies. We just measure how much the flux rises. So we have the here, if we can, yeah, the detection rate, where we have as important parameters the distance for the supernovae, also the luminosity, the mean energy of the neutrinos, and the efficiency of the detectors. The detector configurations that I'm using is IceCube, regular IceCube with the optical modules, and then the high quantum efficiency modules that are in the deep core, so more densely populated area of IceCube where we have more and better optical modules. Then I'm also analyzing IceCube Gen 2, where we are including 9,000 more optical modules, which are in this case multiple MDOMs, which stand for multiple PMTs in each module. And then I'm also analyzing another technology, which is called the wavelength shifter technology, which is basically enabling us to see not only the optical part of the Cherenkov light, but also the UV part of the Cherenkov spectrum. So my explosion model, where we have a quark star remnant, would look something like this. So this is the full supernovae luminosity spectrum. As I mentioned, I have here the first collapse from regular supernova. So the core collapses, then the luminosity of the neutrinos goes high, and then we have an accretion phase. And after a few seconds, or tens of seconds, we have another collapse. So this second collapse, or this second emission, is from the second collapse, which is the phase transition emission. And you can see from this plot that the luminosity is almost one order of magnitude higher. So this can already makes us think that if we can see the other one, this one is probably going to be seen too. And if we zoom in just in this phase transition emission part, we can see here with the different neutrino flavors, and the more interesting one is the electron neutrino, which is the blue, that the luminosity will look something like this, and this behavior here where the luminosity goes up and down and up and down and rings comes from the quark star after being formed. It expands and contracts again a couple of times after it stabilizes. So we see this ringing, as they call it here in the luminosity, which is super interesting because we can know things about how the neutrino spheres are being are moving while the quark star is forming. And here we will have, after the formation, the cooling process and the zero luminosity. So how did I go about my analysis? I used Asteria to simulate the detection. So I have a signal hypothesis, which is my model, my luminosity model, and then and also null hypothesis, which is taking my model, cutting the spectrum in the frequency so that I can take away the peak. So we will see the blue line, which is just a mimic supernova model, but without the phase transition. With this, here I show a 25 kiloparsecs supernova, which is already covering our whole galaxy. And for the different detector configurations, I have IceCube, Gen 2, and Gen 2 plus wavelength shifters. We can already see that this feature stands up from background or no feature supernova very well, so it can be distinguishable. Then I basically take the peak as my test statistic value and perform a test statistic where I calculate the probability of the test statistic value, so the peak, to be in the null or signal hypothesis. And this is important for calculating the detection significance, which is basically the same, but is transforming the probability into a zeta score to see how many standard deviations we are from the mean under the null hypothesis. So the most interesting part is this plot, where we can see that for IceCube in blue, we can see the feature up until the galaxy edge and a little bit more, so 25 kiloparsecs here, with a confidence level between 5 sigma and 3 sigma, where the bands also are the 16% confidence level, 50% and 84% confidence level. Then with IceCube Gen 2, we go far to the Large Magellanic Cloud, where the 1987 supernova was seen. And with Gen 2, with wavelength shifters, we are going over the Small Magellanic Cloud. These three regions are basically, well, the Large Magellanic Cloud and Small Magellanic Cloud are star-forming regions, so it's a part of the sky where we expect to see supernovae happening. In conclusion, basically, we feel that this can be seen even at high distances. However, as we all know, as we already been said, the likelihood of seeing a supernova is not that high. In the Milky Way, is one every 100 years, roughly. We only have seen one with neutrinos, the supernova 1987. And then we also take away that next generation detectors can enhance our detectability of these sharp features, sharp because they are really small in time. Then we will be able to find out things about how the phase transition happens and get part of the phase transition diagram in QCD solved. So the part of the QCD diagram that we cannot calculate with lattice QCD because we don't have enough computational power. And one day, maybe we can discover these new compact objects. And that's it.
Thank you, Maria.
Thank you.
Questions? Yeah.
A very quick question. Thank you for a nice talk. Do you think the binary neutron stars will have a higher probability to?
Sorry, I cannot hear you.
Wait. Do you think the binary neutron star mergers will have a higher probability to experience like the phase transition of the?
Yeah.
Because they have more massive remnants, and
I'm not sure about the probability of them performing the phase transition, because I have not looked into this topic. I focus on the supernova part of it. But the phase transition is believed to be, so after the shock wave of the first collapse of the supernova finishes, instead of reviving the shock wave with a neutrino-driven wind, this is another way of reviving the shock, which is only theoretical and we don't know much about it. Only a few people is studying this. So I guess it could happen in neutron stars, but I wonder how well we could distinguish that, or if the supernova, or if the neutrinos, though I don't even know if there would be a neutrino signal. I don't know. Maybe because the neutrinos are not formed in the phase transition. They are there already, but the phase transition just lets them escape by triggering a secondary shock wave. So I have no idea about neutrinos in neutron star mergers, to be honest. I cannot answer.
Basically, it's similar as the collapse of the remnants and then have a secondary shock.
If the neutrinos were there, probably.
Yeah.
How well do you know the timescales from the first emission and then the second emission from the phase transition to the quark phase?
Yeah.
Is
So
something, yeah,
it's about a few seconds. So yeah.
So that can be estimated theoretically.
Yeah.
Yeah.
It depends on the model, because there are many models, and it depends so much on how you pinpoint the specific of the equations of state. Also, worth to mention, sadly, let me go through this. The phase transition diagram in the QCD is really unknown. We only know the parts of the phase transition diagram where the density is roughly 0. And in astrophysical sites, obviously we don't have densities going to 0. So it's a huge unknown. Where it's 0, it's supposed to be a crossover, but we think that maybe it's a first order phase transition when it's not 0, the density. So it's also an unknown, because we don't know if that's true.
Yeah.
Okay, okay, the 3 sigma and 5 sigma is just a forecast, right?
Yeah, so it's like 3 sigma and 5 sigma is just where the detection where we have the most confidence.
Okay, so I think, so what's the free parameter of your model? So it is the efficiency parameter? How can I say, okay, I found the 5 sigma evidence? What parameter?
Yeah, so when using Asteria, you are simulating the volume of the detector, and you're not simulating specific particle interactions. It's more how the flux will increase. So you basically input the energy, the mean energy of each neutrino, the luminosity, and the root square mean energy. And then you also input the detector configuration, and you simulate the volume. So I don't know.
I need one parameter.
Yeah.
Yeah.
Is this actually just for usual quark collapse supernova, or is this plot showing this, I mean, the search for this particular effect of a quark star?
This plot is showing how well you can distinguish if you get a supernova emission.
So you assume you have a supernova.
Yeah, you're assuming you
Okay.
have a supernovae depending on the distance. So in those ranges, and then you are seeing, okay, does this supernova have a phase transition or not?
Yeah. And so you see like this.
Yeah, can we
light-
see the second peak or
Okay.
can
So
we?
I guess this is the parameter.
Yeah.
Right? Yeah. Okay. Let's thank Maria again. Very interesting.